Good afternoon. I think there's too many announcements. There's a Kappa up, Kappa 10, Kappa 11. Where are we at now? I don't even remember. 10, I think. And there's a new reflective writing question up, so have fun with those this week. Other than that, we can continue to move forward. Don't forget to do the attendance if you're in person today. I'll close this down in a couple minutes. So we spent yesterday, and by yesterday I mean Friday, talking about kinetic theory of gases, trying to relate microscopic quantities like velocities of particles to macroscopic quantities like pressures and things like that. We're now in a better position to also talk somewhat about specific heats. So let's go back to specific heats. And recall, we had two of them. We had a C sub V and a C sub P. And these were defined in the following way. Q equals Cm delta T. Or that's the mass version. If you like moles better, and I'm guessing not many people in this room do, I'm certainly not one of them, you could have the C mole, the molar version of that specific heat, times N, which is the number of moles, times delta T. So just how you want to break that down and count what you've got in kilograms or in moles. Same basic idea though. Right, N number of moles. As opposed to big N, which is the total number of particles in your gas. So I'm not even sure we wrote this down last time. The units on C mole are joules per mole Kelvin instead of joules per kilogram Kelvin. Otherwise, it's exactly the same kind of thing. Okay. But you might remember from last time, we were talking about isothermal expansions, or maybe even 2 times ago, maybe that was last Wednesday, we were talking about isothermal expansions. And I made a claim on my isothermal expansion. And my claim on the isothermal expansion was that if you change the pressure and temperature and volume in such a way, change the pressure and volume in such a way that the temperature doesn't change, that implies that the total energy change of the system is 0. Right? We wrote down some tracks that looks like this. Right? Each one of those is an isotherm. We derived the quantitative formula for those tracks. It was basically just a 1 over P proportional to 1 over V track. And as you go towards higher temperatures, you're going higher up on in the diagram. That's great. So if you start here on your diagram and you move down to here on your diagram, you have changed your pressure and volume a lot. You have not changed your temperature. And my statement at that time was that you therefore will have also not changed your internal energy. The delta E of that transition along any one of these lines has to be 0. This sets up a problem with the way we've just defined the thing that we just wrote down though. Because let's think about that briefly. But recall, I forgot the C, I should have crossed it out. Recall that if delta T equals 0, that implies not that Q equals 0, right? You might think of this formula and say, aha, delta T is 0, that must imply that Q is 0. In fact, it means that delta E is 0. What is true about Q for any one of these lines? Let's say I go from here to here. My well, let's go back and think and recall. Remember the first law of thermodynamics, delta E equals Q minus W, right? If you have a isothermal process, delta E is 0. What does that imply for Q and W? Not 0, equals Q equals W. They must be equal to each other. It's the only way you get delta E equals 0. Let's go back and look at that transition we were just thinking about. You start here and you change to go all the way. Let's make it extreme. Let's go all the way out here to the other end. What is true of W for that transition? The work done as the volume has gotten bigger. Is it positive, negative, or 0? The work done in going from here to here. We've increased the volume from about 1 liter to about 9 liters. Has to go up. Anytime your volume goes up, work is just P times delta, integral of PdV. If volume change is positive, your work done is positive, period. If your volume change is negative, your work done is negative. If your volume change is 0, your work done is 0. It's the way that has to work on that diagram. We also know that along that curve that Q equals W. So what's true of Q? It also has to be positive. And rather large. There's a lot of Q going into this to keep the temperature the same, even though you're allowing this gas to do all this work to expand its volume. Those have to be the same, in fact. Whatever work is being done by the gas, you have to add that much heat energy to your system to keep it at the same temperature. So Q is very much non-zero, and yet delta T is 0. How can we possibly reconcile that fact with that equation that we've been using now for 2-3 weeks? That's not entirely true. So the thought was maybe we assumed that no work was being done when we wrote that equation down. It would be better if we had written delta E equals Cn delta T, or Cm delta T. That would be a more logical thing to write down, because that really is an equivalent. If delta T is 0, delta E is 0. But it's something a little more subtle than what you just suggested. What you said is not way off, but it's something a little more subtle than that. And I'm not sure it's even explainable in a sentence, but try. Yeah, we had put a CV in there and a CP in there, and we said these are probably the same for metals, but probably not for gases. But yeah, you're right. We were sort of, by putting a subscript in there, we were saying, well, we're sort of assuming that this goes in a particular direction. And those isotherms are neither constant pressure, nor are they constant volume. So there's something wrong with this equation anyway, because really it's got to be one of those two. So let's think more carefully about how this is all going. Here's another way to think about this. If you've got two curves, let's see, here's a PV diagram. This might be two different temperature curves, right? Right, this is T1 and this is T2, and everything along that curve is the same temperature, and everything along the curve T2 is the same temperature, and T2 is higher than T1. This is also energy curves, right? Every curve along this has the same internal total energy. That state variable of total internal energy is the same along these curves. You can imagine going from curve 1 to curve 2, in other words, changing the temperature of your gas in any number of ways, right? You can imagine starting at this point and doing it at constant pressure. You can imagine doing it at constant, sorry, that was constant pressure. You can imagine doing it at constant volume. You could imagine doing it at some other random, non-constant. All of those tracks take a gas from an initial energy and temperature point to the same other initial temperature, final temperature and energy point, with vastly different Q's and W's, vastly different P's and V's, right? Again, it's hard to believe and imagine that these two curves, this one and this one, lead you to the same temperature. One of them has a positive network done, one of them has a negative network done. One of them, you're adding energy to the system by some hotter thermal contact. One of them, you're removing thermal energy by some colder thermal contact. They both lead you to the same temperature and same internal energy. So why is it that we're relating Q to delta T? We really shouldn't, but Q really does mean Q. It means the heat added. Sometimes it can be negative. Even though you're increasing the temperature, that Q can be negative. So what's going on? Let's think about these various cases. Let's think about this constant volume one. Let's think about changing from one temperature to the other at constant volume. We have some picture of what that looks like now on our PV diagram. So let's do the thought experiment for doing that. So let's do constant volume. Oh, I'm gonna go back to black. We know that delta E is Q minus W. We also know in the constant volume case, what's the work? Oh, sorry, constant volume is this one. Is this one. That's the constant volume one, right there. What's the work for the constant volume case? 0. If you are not changing your volume, you are not doing work. So what's Q? Oh, right. So we know that delta E is not 0 now because we are changing the temperature. This is where things kind of make sense. We're not doing any work. So all of that is Q. Delta E is Q. And that is CV and delta T. Let's keep it in molar things for now. This sort of makes sense, right? Here delta E is Q, so we don't have to worry about the work being done. So we can solve this for CV. CV is delta E over N delta T in terms of things, in terms of state variables. How about constant pressure? V changes now. So this is this curve, this line right here. Pressure isn't changing, but volume is. So work is not 0 anymore. Work is not 0. But it's still true that Q equals CP delta T. How is that possible? We know that the Q is going to be different in going from one to the other. It has to be. Delta E is the same, but W is changed, so Q must be different also. We know that delta T is the same. It must be true that that CP is different than that CV. They must be different physical quantities. That's the only way to make this make sense. The specific heat at constant pressure must not be the same as the specific heat at constant pressure. Q is different. Delta T is the same. Therefore, CP must not equal CV. Those must be different physical quantities. Okay, we know that delta E equals Q minus W. That's our first law of thermodynamics. Therefore, Q was really delta E plus W, and that must be equal to Cp and delta T. Solving this for Cp, we get Cp equals delta E plus W, it's a terrible W, divided by N delta T, which is similar to, but not exactly the same as the thing we got for Cv. Which must be bigger, Cp or Cv? Cp, why? You're just adding on a work term. It's exactly the same, delta E over N delta T, delta E over N delta T. There's another term here, plus W over N delta T. And you're moving from hotter and cooler temperatures to warmer temperatures. That work is going to be positive. Moving to the right on the PV diagram. And so this whole term must be bigger than this whole term because this is positive. So it must be, just by thinking about this, that Cp is greater than Cv. It must be larger. It has to account for both the changes in total energy that are occurring and for the work that you're doing by, right? Think about this. As your volume, as your gas expands, it's doing work on its surrounding. It's losing energy. And yet your total energy gain must be bigger, and therefore the total Q in must be bigger. And so you need more Q to enact the same delta T. And therefore that Cp must be bigger. It has to account both for the fact that your energy, total energy is changing, and for the fact that your gas is doing some work and therefore losing some energy by doing that work. So it takes more heat energy in to enact that same delta T if you're changing by constant pressure, by increasing the volume. We also know that at constant P, it's true that work, which is in general equal to PdV, if P is constant, you can pull P out. That's just P times delta V. So you can change work to P delta V. Cp really is delta E plus P delta V, which is nice because work, oh, that's not W, P delta V. Work is not a state variable. P and V are state variables. We can do this just in terms of state variables. We also know for an ideal gas that P delta V is equal to NR delta T if P is constant. So you can plug those in and find that Cp is delta E plus NR delta T divided by N delta T. Which is interesting. Let's separate these two terms, because you've got a delta E over N delta T plus a term where all the N's go away and the delta T's go away. It's just R, the gas constant. But we also know something else. What's delta E over N delta T? That's CV. CV, we defined delta E over N delta T. That's just our CV term. CP equals CV plus R. The ideal gas law and our knowledge of thermodynamics tells us what CP and how CP and CV have to be related. We can even say more. If we insist that our gas be monatomic, what do I mean by monatomic here? I mean no molecules, single atoms only bumping around in your gas, which we know isn't true for like the air we're breathing right now. That's okay. We can generalize this in a minute. The only internal energy is due to translational kinetic. In other words, if you add energy to a system, the only place for that to go is into making your molecule or your atoms move faster. It turns out if you have molecules, some of that energy can go into making them vibrate more or spin more, or there's some other degrees of freedom, interesting degrees of freedom that come about when you have molecular systems, where some of that energy can go into that energy as opposed to just moving them around the gas faster. For polyatomic gases, I'm going to put this in a parenthetical statement, so we'll come back to it. Polyatomic, meaning molecular gas, there is energy stored in rotational and vibrational modes of molecular bonds. Okay, so let's stick with the monatomic, not monotonic, monotonic. Okay, consider a gas of N moles. Which I guess we've been doing anyway. Keep the volume constant. Add heat. We know that Q, this is the constant volume case. If you want to show a picture, again, it's kind of nice to see keep a picture in the back of your head about what's actually happening. Sure, we know how it's going to move on the PV diagram. If you add heat and keep the volume constant, it's going to move up in the diagram to a hotter temperature. What does that look like, though? Well, again, we've got this gas cylinder, and we've got some movable piston, but we have pinned that piston in place. So the lid can't move up or down. We can add as much shot or remove as much shot at the top as we want to. It doesn't really matter. We put it in contact with a thermal reservoir on the bottom that is hotter than our gases. Thermal energy will diffuse into our system, and we will heat the gas. At constant volume, it will move up in this diagram. The pressure has to go up. As these things move faster, the volume is not changing. We know in this case that Q equals NCV times delta T. And we know also that that's equivalent, since no work is being done, to the total energy change of the system. We also know from above that CV equals delta E over N delta T. We also know from last Friday's class, the kinetic energy of the particles in the gas is equal to 3/2 nRT. If all of that delta E goes into changing the kinetic energy, then it's true that delta E must be the same as delta kinetic energy, which must be 3/2 n times delta T. This is where the monatomic is important, because if there is that energy is going into vibrational and rotational states, that first equal sign won't be there. Some of that energy will be going into something else. So we can make CV therefore equal to delta E, we know is 3/2 n delta T, divided by n delta T. The n delta T's go away. I forgot the R up here. I also forgot the R here. Sorry about that. For a monatomic ideal gas, now we know how CP and CV are related, we know what CV is. It's 3/2 R. It has to be. For a monatomic ideal gas, CV is 3/2 R. If you want to plug that in a calculator and get a number, it's 12.5 joules per mole Kelvin. And since we know CP is CV plus R, CP must be 5/2 R. Or what do we get to? 20-ish joules per mole Kelvin, something like that? I don't know. We can calculate what the specific heats for a monatomic ideal gas have to be just based on the physics of what's going on. And they're vastly different, right? So when you talk about this equation, what's the bottom line here? Well, it's important to see how this all works out. It's important to see how these specific heats are related, but only in the sense of how we've defined specific heat being related to the heat we've added to the system, and not the total energy change of the system, right? Be aware when you're using these equations, Q really means Q, the heat that you've added to the system, and not the total change in energy of the system. Delta T really is delta T, but C will change depending on how you go from one temperature to the other. It is CV if you go along a perfectly volume constant line. It is CP if you go along a perfectly pressure constant line. And it's neither the above if you go in some other way. You're going to have to find some other C or define it some other way, or you can't even use this equation. Okay. Let's think about polyatomic gases. Some of the energy that you add, some of that thermal energy that you add, instead of going into the translational kinetic energy, instead goes into vibrational states and rotational states and things like that. Because if you have, you know, even a nitrogen 2 atom or an oxygen 2 molecule, you can actually, it's like you can think of the molecular bonds as kind of like a spring system, and you can imagine loading more energy into that spring system by making that thing vibrate faster. It's basically just a spring-loaded system. You can make that thing rotate faster in a couple of different axes. And the more complex you make your molecule, the more of those individual vibrational and rotational states exist. So some Q, or I'll say some delta E, goes into exciting other aspects of the gas. Need to worry about something called degrees of freedom. So what kind of degrees of freedom are we talking about? There are several different kinds. We've already talked about translational degrees of freedom. These are the degrees of freedom of your atoms and molecules to move around in your gas. And since we live in three-dimensional space, normal gases operating in a normal way have 3 degrees of freedom of translational motion: forward, backwards, left, right, up, down. These are the 3 spatial dimensions. You also have rotational, usually 2 or 3 for simple molecules, but this actually usually 2 or 3. Vibrational, these can be a lot. Others, who knows? To give you an idea about how this works, I have a PowerPoint slide. I don't know if any of my, oh yeah, here it is. This is good. So here you go. For instance, a water molecule. What are we talking about? You know there's obviously the thing can move around. They get 3 dimensions of degrees of freedom that way. Turns out there are 3 vibrational degrees of freedom for a water molecule, and you can see them here. It's all the ways you can think about jiggling this thing in a way that's going to make those springs act in a normal fashion, right? So those are the vibrational. And the rotational ones are, I think there's 2 of them. You could imagine spinning it this way, and you could imagine spinning it this way. Those are 2 axes of symmetry about which you could spin this thing and have it do the thing. But if you have a complex molecule, right? How many degrees of freedom does that thing have? Hundreds, probably, right? This gets very complicated very quickly, right? Every single pair has different ways that it can vibrate, and they just add exponentially as you make the thing bigger and bigger and bigger, right? So things like water molecules, you might be able to break it down. This has a degree of freedom, 3 rotation, or 2 rotation, 3 vibration, 3 translation. That gives you 8 or so, right? That's a simple molecule. This thing could have hundreds of degrees of freedom. So it gets very complicated very fast. So this one is purely monatomic. You only have translational. All of these are possible with polyatomic. Let's let F, lowercase f, be the total degrees of freedom of molecules in your gas. All the F's, all the 3's in our previous equation for the specific heats become F's. The 3s go to Fs. So for monatomic and polyatomic, your equations look like this. You've got a CV here. CV is 3/2 R. And CP is 5/2 R. This is what we've written down before. In the polyatomic case, this is just F over 2 times R. This 3 really was the degrees of freedom of our gas. You might even remember that 3 came into our equation when we were thinking about, okay, but we've got an X, a Y, and a Z component of that velocity, and we added them all together, and that gave us a factor of 3. So that now becomes an F, and this, of course, has to go to an F plus 2 over 2 times R. Interestingly, you can now work backwards to figure out what the degrees of freedom are of your gas. Add a bit of energy to it, hold the volume constant, let it change in temperature. You can work backwards to figure out how many degrees of freedom are in your gas by figuring out what the temperature change actually was from that given amount of energy. And this is complicated because if you have a gas that is entirely made of these crazy molecules, then you expect the total degrees of freedom of the gas to be the degrees of freedom of this crazy molecule. But what if your gas is made of lots of things, and some of it is simple hydrogen atoms, and some of it is molecular things of simpler nature, and some of it is that? Can you think about an average degree of freedom of your gas? Yes. Change the temperature, see how much, add heat to your system, see how much the temperature changes without changing the volume. You can backtrack to figure out what an effective F for your gas, which will be some combination of the Fs in your gas and how much those gases actually contribute to your overall consideration. So you could, even though F itself has to be an integer, really, it is true that you can have an effective degrees of freedom of your gas that is not an integer if your gas has lots of different stuff in it. Okay, that's all I need to say about specific heat. But this is confusing. The way you define specific heats, just to backtrack and give you the overall picture of the last 45 minutes of class, 40 minutes of class, the way we defined CV and the way you define specific heat, you might think that changing the temperature is solely related to how much heat you add to the system. It is not the case. Delta E is really a much better temperature of delta T. If delta E is 0, delta T is always 0. We define it in terms of Q for ease, because if you're talking about a metal blob on your table and you add a delta Q to it, you can't keep the volume constant, right? There is something else going on there. And so we think about you can't think about the work difficult to think about the work that the metal is doing as it expands into space. We think about the heat that we're adding only. But in doing so, we need different definitions for C depending on how we get to that new temperature. And so just keep that in mind with all of this stuff. Okay, we're certainly not done with this part of there's one more. So we have tackled changes in our system by constant volume, by constant temperature, by constant pressure. There is one more that we wrote down at the beginning of this section as an important process where we need to think about that happening. And that was the adiabatic case. You might remember that adiabatic expansion the definition of an adiabatic expansion is one where no heat is added. It's all work and no heat. Q equals 0. What can we say? Okay, the other ones were pretty simple. We were able to write down almost immediately what the implications were for various things. Adiabatic's gonna take us a little more work to get there, but it's no less important. Let's go ahead and do the work to get there. So let's change the pressure a little. What happens to T and V? By the way, we could do this. We could say what happens if you change the temperature a little, what happens to P and V if you change the volume a little, what happens. So that you could do this either way, but let's work with P. It's a little bit simpler to get there, and the math comes out a little bit nicer. Start with ideal gas. We know that PV equals nRT. And again, we're going to change P by a little bit. So we're going to want to take a derivative of this thing with respect to P and see how the other things are changing. That's going to give us an idea about how everything is going to pan out. So take ddP of the whole thing. We get ddP of PV equals ddP of nRT. Again, why are we doing this? We want to know how a small change in pressure is affecting both sides of this equation. Okay, well, we can expand. We can do a product derivative on the left-hand side. We get, if you remember your product rule, or just the chain rule, V times dP dP plus P times dV dP equals, and the nice thing on the right-hand side, there's only a single variable that's changing, and that's the T. We can pull the NR out, and we get NR times dT dP. Close this guy. It's just in the way now. Great. All right, here we go. Also, we know that Q minus W is equal to dE internal, which is equal to F over 2 times NR dt. We also know that this is just the negative of the work. Because Q is 0 for an adiabatic process. We also know that the work is negative PdV, or the negative of the work is negative PdV. So we can take this and solve for dt. We know that dt equals negative 2p over F and R times dV. We can divide both sides by dP. It always amazes me, I'll be honest. Right? Why is it that you can just divide by a dP and that becomes calculus and a derivative? It just works. I'm happy to do it. I still don't really understand it. It's crazy. So we can plug this into here and get rid of our T's and have an equation that's only in terms of P's and V's. That will be useful. So plugging in, we get that the dP over dP is also 1. That goes away. We have V plus P times dV over dP equals NR times this whole mess, negative 2P over F and R dV dP. The NRs actually cancel out. That's kind of nice. We get V plus P dV dP. It gets fun to say after a while. Negative 2 over F times P times dV dP. Solve this straight for V. V equals negative P dV dP And that's in both terms. You got a 1 plus 2 over f. Okay, we can start thinking about separating variables now and actually solving this thing. Let's do it. Let's bring our p's over to the left and our v's over to the right. We get dp over p equals negative dv over v times 1 plus 2 over f. Let's just expand this thing out. I'll do the intermediate steps. Negative dv over v times f over f plus 2 over f, and then we can make a common denominator. That's negative dv over v of f plus 2 over f. Okay, let's make a definition. Let's define gamma to be f plus 2 over f, because it's going to be a lot easier to write gamma than it is to write f plus 2 over f. So we have this rather simple looking equation. dp over p equals negative gamma times dv over v. And now we can just integrate. From some initial to some final pressure, from some initial to some final volume. And we get dp over p, dv over v, they're the same integrals. You get the log of that, the log of p, natural log of p, and evaluated from the initial to the final, equals negative gamma times the natural log of v, evaluated from initial to final. So this looks like ln of p initial, final, minus ln of p initial. Ln of pi is equal to negative gamma times ln of v final minus ln of v initial. And we're almost somewhere profound. Stick with me for just a second. Using what we know about logarithms, if you have difference between two logarithms, you can make that a ratio of those quantities inside the logarithm. Let's do that. We have the log of pf over pi equals negative gamma times the log of vf over vi. The magic of logarithms. And if you have a multiplicative term in front of your logarithm, you can move that inside your logarithm as an exponent. So we can really make this ln of pf over pi is equal to ln of vf over vi, quantity to the negative gamma. And now you can take e to both sides and get rid of the logs altogether. And you get pf over pi is equal to vf over vi raised to the negative gamma. Or if you prefer proportionalities better, p proportional to 1 over v to the gamma. Both of those are box-worthy equations. Also true, if you want to turn this around, that v is proportional to p to the negative 1 over gamma. If you have an adiabatic process and you change its pressure, you know how much the volume will change now by, and vice versa. If you know how much the volume changes by, you can calculate how much the pressure will change. I should also point out, in the minute that I have left, why this gamma thing is kind of important. Remember, we defined gamma to be f plus 2 over f. Does anybody know what that is also equal to? F plus 2 over f. F plus 2 over f. F plus 2 over F. Can you imagine combining these two things to get F plus 2 over F? You should be able to imagine combining those two things to get F plus 2 over F. What's CP over CV? CP is F plus 2 over 2 times R. CV is F over 2 times R. R's go away, 2's go away. The ratio of the specific heats. That's what gamma is. It has some physical meaning, it's important, and it's related to the specific heats of the thing you're talking about. So this is the ratio of the specific heats. This has to be CP over CV. So gamma, we didn't just make that definition by chance. It's an important quantity. It's the ratio of the specific heats, and it's related specifically to how many degrees of freedom are in your specific gas. If you have a monatomic ideal gas, that F is 3, sorry, and that's just 5/3. That is what gamma has to be for a monatomic ideal gas, always. All right, good. We'll pick this back up on Wednesday. Uh-oh, somebody chatted me. Ah.